Okay, so let's go to page 9. So we spent the last 2 days going over area, really kind of practicing and getting used to the orientation of finding area, whether it's top minus bottom or right minus left. I think naturally we just understand that top minus bottom is going to feel easier because equations are usually set up in the form that is where it's ready for you to insert into the formula. But right minus left, it's just always going to be a little more work involved because the equations are usually not going to be set up in the proper form. You have to rearrange the equation if you want to do right minus left. So we'll continue to remind us of that because today we're talking about volume, but we're going to start with the easier top minus bottom orientation, and then we'll kind of practice and reintroduce right minus left. But hopefully yesterday, through that activity that we did with the FRQ, looking at region R, region S, and all the different variations, we can kind of use that as foundation for what we're going to be building on today with this method. Okay, so let's start off with a review. We're going to talk about area again, and then we're going to talk about how we're going to take this area formula and adapt it so that we can create a 3D object calculation dealing with volume. Okay, so the basic idea is that we're always going to be rotating around an axis. We're going to take a shaded region, we're going to rotate it, and because we're rotating, it's always going to create a circular shape. So there's always going to be this area of circle that's involved whenever we're finding the volume. So right now we're only finding volume for circular-based objects. Okay, circular-based objects. So let's start with just solving this problem that we already know how to do, and we'll talk about how we're going to build on this to get to a volume calculation. Okay, so recall finding area under the curve y equals square root of x. That's this radical function here. I'm going to name that. Between 0 and 4. So I'm going to create a shaded region. Now, if I want to find area, I know that this is I can think of it as a top minus bottom because we see that the curve is always above this y-axis, this x-axis, y equals 0. So we're going to draw a representative rectangle. So imagine we're just finding the area of this region by adding infinitely thin vertical rectangles from one end all the way to the other end. Okay. So here's our area. Area is top minus bottom. What are the bounds going to be? 0 to 4, right? X values from 0 to 4. As far left as you can go and as far right as you can go. Top graph, we ask ourselves, what is the top of the rectangle touching? It's touching the curve, right? So we know that's the top graph, the root x. Top minus bottom. What is the bottom of the rectangle touching? 0, the y equals 0. Okay, you don't have to, for on the test, if you don't have to put that 0 there, I just want to kind of do this for demonstration purposes for now. Okay, if we want to work this out, we can go through power rule, plug in the upper and lower bound, or use our calculator. But either way, it's going to come out to be area being 16 over 3, okay, and then units squared to indicate that this is a two-dimensional area calculation. Okay, now this is what I want to kind of focus on. Okay, what we found is area related. Okay, think of the root x minus 0 as a representative height of a rectangle. Okay, the reason why it's a variable is because it's adapting to all the different heights of this rectangle, right? Root x minus 0 is going to be different than root x minus 0 over here, right? It's adapting to all the ever-changing height of these infinitely thin rectangles. The dx is going to represent the width of these individual rectangles, okay? But we're not doing any of the calculations, right? We're just plugging into the calculator. We're making the calculus do the work for us, okay? But we're arriving at the exact area. But just want to make sure that we see the fact that this is 2 dimensions, right? This is width and height, that's 2 dimensions, and that's how we're able to arrive at area of a rectangle, or areas of rectangles added together. Okay, so we clearly see those 2 dimensions, okay? And now we're going to adapt this to get to that 3rd dimension that we need to get to a volume calculation. Okay, so essentially the integral notation allows us to add infinite numbers of differently sized rectangles to form the area calculation. Okay. Now with this method, we're going to take this region here. Okay. We're going to create it by the f of x and the x-axis and rotate this function 360 degrees around the x-axis. Okay, so we're always going to be rotating around a line. Okay, but right now we're going to just rotate around the x-axis. We'll start with the easier ones. Okay, and then what shapes do you see if we were to separate the resulting object into thin slices? So you kind of imagine, right, that if we were to take this shape and rotate it around the x-axis, this is what's going to come out of it, right? We can kind of imagine it's going to create kind of a bowl-shaped object. Okay, we're never going to have to draw these objects. We just have to understand how to pull certain information from it, put into the formula, and get the volume. Okay, but right now, I just want to kind of help you visualize what we're finding as we're putting this formula together. We're rotating this shaded region around the axis in the 360-degree manner, and you can kind of see that this is the object that's created. But just like how before, we're adding infinitely thin rectangles, now we're going to be adding infinitely thin circular discs, right? Kind of imagine these as these circular discs. Okay, so we're going to do the same problem here, or at least the setup, okay? And then, let me see here, resulting objects in the thin slices, the answer is going to be circles. Okay, so right now, we'll call this root x again. We're rotating around the x-axis. We call that the axis of revolution. So I like to use different color pen, but either way, I'm always going to use dotted line to indicate that's a special line for us. We want to think of this as the new center of our object. As we rotate, you kind of imagine that axis is going to be right at the center of the object. Okay. AOR represents axis of revolution. And it's going to be right at that line, y equals 0. Okay. Now, we're also going to draw this distance between the dotted line and the boundary. But now this is no longer going to represent the height of a rectangle. This is now circle related. So any idea what this now represents for the circle? Radius. Yeah, it's going to be called the radius. So now we have a representative radius in place. Okay, we're adding infinitely thin circles. So we have radius that's going to be plugged into the area formula of a circle. And then, but the idea is the same, right? Which is we're adding that 3rd dimension. We're creating a different shape, but it's still the same idea. Okay, so if we were to kind of break this apart here, if we want to just look at one thin slice, we can kind of see that circular disc, 3-dimensional circular disc. We can call this R of x. We want radius to be a function. So right now, we're going to have uppercase R and lowercase r, but right now we're only going to deal with uppercase R. Next section, we're going to have to deal with holes in the graph, and we'll have a second radius to be involved. But right now, we're just going to have one radius, but it's going to be uppercase. So you can see that this is the face of this object is a circle, right? You guys remember what's the area of a circle? Formula. Pi r squared. Okay. So this distance is the radius. We're going to call it r, big R of x. So area is going to be pi big radius squared, right? So you see that we're adapting the area formula for this particular format that we'll be using. Now we know the area is already two dimensions, right? Area of a circle is already 2 dimensions. And then there's going to be a certain width for these circular discs that we're going to call dx. And then when we attach that dx, that's going to give it that 3rd dimension. So area is already 2-dimensional, times that dx is going to give it that 3rd dimension. Up here, though, it's just height times width. So that's why there's only 2 dimensions here. Okay, but here we have 3 dimensions. And now we're going to adapt it into the volume formula. Okay, this is the area of one representative circular disk. But we want to add infinitely thin circular disks from one end all the way to the other to create this object. So here's our formula. Pi big radius squared. And the integral from a to b is going to accumulate all those thin disks from one end to the other to achieve the exact volume of this object. Now, typically, we like to put the pi out in front because it's a coefficient. So this is more the formula that we're going to be using over and over again. Okay. Okay, so right now, we're just going to focus on the easier orientation, where our axis of revolution is going to be horizontal, and we're going to be creating these vertical radius to make it easier to create this top minus bottom problem. Okay, and then once we get comfortable with that, then we'll move into horizontal radius with a vertical axis of revolution. Okay, so radius we're going to call big R of x or R of y, but right now we'll just do R of x to isolate just the top minus bottom. And then the distance from the axis of revolution to the boundary of the shaded region, that is, before we call that distance the height of the rectangle, but now we're going to call it the radius. Okay, so now we're really going to solve this problem that we have kind of worked out or just identified. Okay, but now we're going to find the object, the volume of this object for this problem. Okay, so back to our first diagram. Okay, y equals square root of x from 0 to 4. Axis of revolution being the y equals 0. Rotation around this y equals 0. And that dotted line is there to, again, we don't have to draw the picture, but just want to keep reminding us that the dotted line is the center of the object. It looks like it's at the edge, but after the rotation, this dotted line is always going to be the center of your object, right? It's going to be an object that looks like this, right, or this. Okay, so the next step is you want to draw the radius. Okay, so it doesn't seem like a big deal right now, but I want us to get in the habit of doing this. If we can build this habit, I think that will lessen the chances of making mistakes later on. Whenever you draw the radius, okay, always put your pen or pencil on a dotted line first. Okay, again, it doesn't seem like a big deal. It's like, okay, you're just connecting that distance. But start on a dotted line, and from the dotted line, extend to the boundary. Okay, if we can build that habit, I think that will prevent future issues. Okay, start on the dotted line and extend. Whether it's up or down. In this case, the boundary is above, so we're going to extend up. Okay. Now that's called a radius. And we're going to build our radius expression. Thanks. Okay. Top minus bottom. The top of the radius is touching the curve, so that's root x. The bottom of the radius is touching the y equals 0. So radius is just root x minus 0, which is root x. Okay, the boundary is already in front of us, so we're ready to insert into our this method formula. Oh, and also, our radius is always going to be perpendicular to your axis. Okay, so there's always going to be a perpendicular relationship between your center of your object and the radius of your object. All right, let's build our volume formula. Pi comes first. Definite integral from x1 to x2. What are the bounds again? 0 to 4. We're going to take the radius expression. I like to use brackets, but parentheses is fine. Okay. Insert your radius into your bracket, and we have to square it, right? Because we have to have this area of a circle built into the formula, pi r squared. That squared has to be involved, the pi has to be involved. Okay, dx. Okay, pi r squared, that's area, that's 2-dimension. Dx is the width, that's the 3rd dimension. So we're accumulating all these infinitely thin disks from one end to the other. Okay, but just making the calculus do all the work. Okay, root x squared, that just cleans up to be x. So eventually we're going to plug in the calculator, but right now this is easy enough for us to just do by hand. Okay, I'm going to leave the pi out of it. I'm just going to do integral of x. Integral of x is a power rule. As this cleans up, root x squared becomes this x, right? Power rule, x becomes x squared over 2. And once you have your antiderivative, you can work the bounds into the answer. Upper bound first, upper bound in for x, minus the lower bound, 0 in for x. Second term zeroes out, first term is equal to what? 8. So 8 is our answer, but we always are going to insert pi. So I'm going to ask you to not enter pi into the calculator. We want to have exact value. So we're just going to put pi next to our numeric answer. As a reminder, we found something that's volume related or that's 3-dimensional, so units cubed. Sometimes the problem will give you a specific unit, whether centimeters or inches or kilometers. If that's the case, then you're going to use whatever units they provide for you. But if they don't provide a unit, just right now, just put units cubed. Okay, any questions so far? Okay, let's do another top minus bottom to get more comfortable with it, and then we can maybe explore the right minus left. Okay, so back page. Okay, I put the formulas at the top for easy reference. Let's look at number 2. Find the volume of the solid created by f of x equals 2 minus x squared. Okay, sorry, I forgot to put the other equation. The other equation is and y equals 1. So we're going to be finding the shaded region between 2 minus x squared and y equals 1. Revolved around the line y equals 1. So anytime you see the word revolved, that tells you that it's about to tell you what the axis of revolution is. So my axis of revolution is y equals 1. I'm going to be rotating around this line. This is the center of my object. Okay, let's draw the diagram first. Y equals 2 minus x squared. That's going to be a parabola that opens down with the y-intercept at 2. So we can just draw it free form here. And then there's also the line y equals 1. So we know y equals 1 is going to be somewhere here. There we go. There's my shaded region, enclosed shaded region. Okay, we're going to take that shaded region and we're going to have to now add in the axis of revolution, which is also at y equals 1. Right now, I just want you to observe the placement of these dotted lines. You're going to see that all these dotted lines are going to be right up against the right up against the axis, or sorry, right up against the flat surface of your shaded region. You're not going to see any gap between the dotted line and the shaded region. Okay, and that's to ensure that we can use this method that we're talking about today. Later, the axis may be in a different place from the shaded region, and that's where holes will be created, and we're going to talk about that with washer method. But right now, just pay attention. Look at all the similarities of all these axes. All these dotted lines are right up against the flat surface of your shaded region. Okay, that's going to be helpful later when we're having to differentiate between different methods. Okay, so now let's draw the radius. We know horizontal axis means it'll be an easier problem because our radius will be vertical. If our radius is vertical, we know top minus bottom will just lend itself to be an easier problem to set up. Okay, so let's build a habit. We'll draw the radius. Put your pen and pencil on the dotted line first, and extend from the dotted line towards the boundary. Okay. Start on the dotted line and extend to the boundary. Okay. We see a vertical radius. Let me name that. That's R of x. Okay, so now let's build our radius. Okay, top minus bottom. What's the top of the radius touching? Okay, so that comes first. Minus parentheses. I always like to just protect that. I know right now it doesn't feel like a big deal, but once there's multiple terms here, the parentheses is going to be really necessary. Okay, top minus bottom. What's the bottom of the radius touching? Y equals 1. Okay, let's clean that up. Combine like terms. 2 minus 1 is 1. Okay, so it looks like we have parts of the formula ready to go. We got pi, we got the radius, we're going to square that. But what else is missing here? The bounds, right? How do you think we can find these bounds for the shaded region? Okay, set equations equal, okay? Right now, we're going to be able to do it by hand, but we're going to move into the calculator as the calculations get more difficult with decimals. But I think right now we can do it by hand. So we're just going to set the line y equals 1 equal to 2 minus x squared. When we find the intersections will also act as the boundaries of our shaded region. Okay, set equations equal. Okay, 1 equals 2 minus x squared. I'll move the x squared over to the left side. I'll subtract 1 to the other. X squared equals 1. Take the what? Square roots. So x equals what? And yeah, plus or minus. Okay. So plus or minus 1 tells us we have two boundaries that came out of it. -1 and +1. So we have our boundary here at -1, and the other one is at 1. Good. I think everything is found. We're ready to use our volume formula. Pi first. Depth integral from left bound to right bound, -1 to 1. Notice everything that we're entering is in terms of x. Big radius squared. So I like to use brackets. 1 minus x squared squared. Right? You always should be able to visualize that area of circle involved in your formula, right? Pi r squared. If you want to work this out by hand, you would have to FOIL all this out. Let's just make the calculator do this for us, okay? So I have on the board something that can speed up the process, especially if we're dealing with problems that have multiple radius. So you can choose to use it or not, but I find it to save a lot of keystrokes, especially down the road. And I have it there, Vars, Vars function y1. Okay. And I'll refer to it when I show you the steps. Okay, vars y, vars function y1. So let's go to y equals. And now, if you're using a 36 Pro, you're just enter everything as you see here without the pi. Okay, just go ahead and enter everything. But if you're using the T84, I want to show you some things that we can do to save time, especially down the road. Let's go ahead and insert that radius into your y1. So under y1, type in 1 minus x squared. Okay, once you have that in, go ahead and go back to your home screen, do second mode to quit out of that screen to your home screen. Okay, go to Math 9. Get your definite integral notation set up. We're going to go from -1 to 1. Again, leave pi out of your calculator. And now, rather than entering in 1 minus x squared squared, we're going to call the function. It's going to be useful, especially if you're having to call the function over and over again. So go to vars. Scroll over to yvars, function y1. Okay. Also, when you use this feature, there's less need for parentheses. I can just square my radius and then dx. 1.066. We can always round to, or we can always approximate to 3 decimal places. But always see if you can try to get it to a decimal or to a fraction. So if you can do math, fraction. If you can convert to a nice fraction, then we prefer that. But if not, you can just go to 3 decimal places. 16 over 5, don't forget the pi. And again, this is volume, so this is 3-dimensional in this cube. Okay. Any questions about top minus bottom and all the steps involved there? Okay, let's explore problems where there's a vertical axis of revolution. If there's a vertical axis, that means our radius has to be perpendicular, which means our radius is going to be horizontal. If our radius is horizontal, then we got to do right minus left. And that's typically a red flag. Okay, if you see right minus left, that just, you want to just kind of prepare yourself for adjusting the equations. Okay, the equations are usually not going to be ready for you in the form that it's given if it's right minus left. Okay, so let's explore those problems here. Example 3. Given the region formed by the function, the x-axis and the y-axis, so here's my shaded region. Find the volume of the solid formed by revolving the region about the y-axis. Okay, so now we're rotating around the vertical line. My axis of revolution is now going to be x equals 0. So let's start off with that. Let's start off with our dotted line. This is the center of your object. We're going to rotate this shaded region around. It's going to kind of create kind of a cone-shaped object. Again, we're never going to have to draw the picture or identify the shape. I just want to visualize, help you understand that this is not the edge of the diagram. This is the center of the object. Okay, this is where the radius is going to be coming from. Okay. Next, we're going to draw the radius. Again, the radius is always going to be perpendicular to your axis. And let's always do this. Let's always start on the dotted line, and from the dotted line, move towards the boundary. Okay, from the dotted line, extend to the boundary. Okay, as soon as you see a horizontal radius, you know that we got to adjust our equations. Our equations are not prepared for a right minus left. This is set up for a top minus bottom, but not a right minus left. So we got to rewrite this equation. We need to get x by itself and not y by itself. So how can I rewrite this equation here? What would that look like? Okay. Actually, I think if we just move some things around, we can't. Yeah, you can definitely multiply by -1 and subtract. But I'm just going to move the x over to the left side, make it positive x, and I'll just subtract the y. Okay. Either way, whatever algebraic step you want to take, you just want that x to be on the left side so that the right side is reserved for the expression that you want to use. Okay. So as soon as you see a vertical axis and a horizontal radius, you know that your equation needs to be rewritten. Okay. Typically, that just leads to a slightly longer step, but that's just something that we saw yesterday, and we're going to prepare for. Okay. And then the other point, the other line we're going to use is this axis revolution. That's the x equals 0. Okay, we should be ready to use our formula here. y1 to y2, big radius squared. Okay, so let's start there. Oh, sorry, let's build our radius first. Okay, our radius is now big R of y. Okay, right minus left. What is the right endpoint of the radius touching? So y minus y that we've adapted and rewritten. Minus the left endpoint of the radius is touching the 0, so there's our equation. Right minus left. Clean that up. Okay, volume formula. Now keep in mind, okay, we're stacking these circular disks from down here all the way to up here, okay? So what are the bounds going to be? 0 to 1. It's the 1 up here, not the 1 over here, right? So I want you guys to visualize that we're using y values. We're stacking in this orientation here, okay? From 0 to 1. Everything that we see we're using y values, okay? Big radius squared. Okay. Again, let's go to our calculator. You may be seeing y's on paper, but in the calculator, make sure that you always use x's. So again, I'm going to just go into my y equals, and I'll just enter in 1 minus x. Go back to my home screen. I can really just go back and adapt what I already entered in, right? Because the y1 can stay, the square can stay. I just have to change the bounds. So go from 0 to 1. But if you want to get to that y1 again, you can go to Vars function y1. Enter, see if you can convert it to a fraction. So do math. 1. It does, 1/3. Okay. Any questions with right minus left? Right. We just have to see that we pull the bounds differently, and we also, the equations that were used have to be in a different form. Okay. We can't use what we have in front of us usually for right minus left. Okay. So why don't we try part B? Similar process, same axis of revolution, Same orientation, see how far you can get, and I'll walk through the steps after you guys had a chance to try it. Okay, so try part B. Now, when you take the square roots, technically there's a plus or minus that comes out of it, but the negative square root is going to live on in the second quadrant. So what we're seeing in front of us is only the positive square root. Okay. Okay, build your radius, right minus left. And then start working in your volume formula. Okay, where are the bounds going to be? 0 to 4, right? You're stacking these horizontal disks from down here all the way to up here, right? We're not going in this direction, right? We're going bottom to top. Bracket, radius, squared, dy. Okay, make the calculator do the work for you. Leave pi out of your calculator and just insert it next to your answer at the end. Okay, what'd you guys get? 8, and then we attach the pi, right? Okay, any questions here? Okay, we'll spend some more time with this method, so we're just trying to get some more practice. Let's go to the next page and start working these practice problems. So page 11. Read the problem, see if you can decide how you want to draw your axis of revolution. Is it a top minus bottom? Is it a right minus left? Can you draw your radius? Can you identify your bounds? Okay. Yeah, so whenever you see the word rotation or rotated about, that means it's about to indicate to you where that dotted line is, where that axis of revolution is. So here it says rotated about the line y equals 8. That should be an indication that we're dealing with an easier problem because we know it's going to be a top minus bottom. Since our radius is going to be vertical, if our radius is vertical, we can just know that our equation is normally going to be set up for us already, and there's no adjustment to the equation needed. Okay, let's build that habit, right? Start on the dotted line and extend to the boundary when you create your radius. So start on the dotted line and extend down. Okay, if we can always start on the dotted line, next section we're going to see it's going to prevent us from making mistakes. Okay. Okay, top minus bottom. What is the top of the radius touching? 8. Okay, what's the bottom of the radius touching? 2x cubed. Okay, so we're going to do top minus bottom, just like that. Okay, what are the bounds going to be? 0 to something that looks like 1.5, but we want to get a more accurate location than just an estimation. So what can we do to get that accuracy? Okay, set the equations equal to each other. So we can try to work it out by hand, or we can make the 36 Pro do num solve. You can do num solve in your scientific calculator, or you can graph it and look for the intersection. So I want us to practice that, especially if you have a graphing calculator. It's also good to kind of build that knowledge of finding intersections using your calculator. So I'm going to go graph the 2x cubed. I'm going to graph the 8. If you do zoom 6, it'll take you to a standard window. And in this case, it looks like it's good enough for me to find that intersection. So for me to find it, you make the calculator do it for me. So I'm going to go to second trace and select intersect. So second trace intersect. It says first curve, so get close to the intersection, but not on it, just relatively close, hit enter, just to tell the calculator, okay, I want you to look at this curve. And then it's going to blink on the cursor, will go to the other curve, but see if you can move away from the intersection a bit. Try not to be too close to the intersection. Hit enter again, and now the calculator will find that intersection for you. It should be a decimal value, 1.587. Okay, looks like everything that we need is found, so we can work in our volume formula here. Again, you want to practice using that y1 notation, so let the y1 hold your radius, and then you can just do y1 squared. And just leave pi out of your calculator. Okay, let's try part B as well. What's different about part B? It's a vertical line, right? Rotated about the y-axis, that's x equals 0. So vertical line tells you that the radius is going to be which direction? Horizontal, right? So as soon as you see a horizontal radius, you have to understand that your equation needs to be adjusted. Okay, they're not going to be in the correct form that you want it to be in. So how can I work or rewrite that 2x cubed? Yeah, good. So we can get that x by itself, right? So divide by 2, and then cube root. That's going to be the right endpoint of the rectangle hitting the curve, and the left endpoint is touching that x equals 0. Okay, what are the bounds for this shaded region? 0 to 8. This case is easier to find, right? Here, there's no, there's not a need for us to go to the calculator. Here, it's kind of obvious. We're going from 0 all the way to that horizontal line, and that horizontal line is holding steady at 8. So 0 to 8, because we're stacking these disks in a different orientation than before. We're stacking from the bottom to the top. Oh, let me build a radius here. Radius is right minus left. Okay, practice entering into your calculator. If you want to get to cube roots, you can do math 4. Doesn't convert to a decimal, so 12.095 pi. Okay, so I shifted all the homework one day over, so tonight's homework is also from 7.1